Hello, and here we go again with AP Bio. We're continuing our look at water and the chemistry of water. So if you remember last section, we talked a lot about how the polarity of water and how it behaves as a molecule gives rise to the different properties that help life exist on Earth. And so what we're going to look at now is we're going to look at water's role in acids and bases and how we can measure pH. So one of the things on the AP National Exam, this is potentially one of the math type problems that they could ask you to do, is to be able to find the pH, the POH, or the H or OH ion concentrations for that. So the definition of an acid, there's three different ones. If you look here, there's the Arrhenius definition, where acids release hydrogen ions in water, bases release hydroxide ions in water. And we've talked about it a little bit, or over the summer you might have, but the hydrogen ion, remember, is H+, and the hydroxide ion is OH minus. And when we put them together, we get water, so they neutralize each other. So that's why acids and bases will neutralize each other. The one that I want you to kind of focus on is right here, the Bronsted-Lowry definition. So a Bronsted-Lowry acid is a proton donor. Okay, it can donate that hydrogen ion. A Bronsted-Lowry base is a proton acceptor. It's going to accept the hydrogen ion and decrease the hydrogen ion concentration. And then I'm not even really going to look at the Lewis acid and base. You can pause the video if you'd like and read through that. And it basically says the same thing. But really, we want to concentrate on what the Bronsted-Lowry is. So an acid is a proton donor. A base is a proton acceptor. So we're really going to be looking at, hey, what's the role of the hydrogen ion in these solutions? So as we said before, an acid is a proton donor, a hydrogen ion donor. And we can have strong acids and weak acids. And strong acids will dissociate completely. Now what that means is if we have something like hydrochloric acid, HCl, in water, that will dissociate completely. We're going to get, for every one molecule of HCl, we're going to get one molecule of hydrogen ions. So if we have a 1 molar solution of HCl, we're going to have 1 molar, that's going to be the concentration of the hydrogen ion. If we've got 12 molar hydrochloric acid, we're going to have 12 molar hydrogen ions in that solution, so it completely dissociates. So here's a way to look at it. So here is COOH, is an organic acid. And what this is here's carbon, double bond, and so there's what makes a lot of salicylic acid, amino acids, acids. And what will happen is this hydrogen will dissociate. It will come apart, and that's what we mean about being a proton donor. And what we end up with is that after the hydrogen is left. And we'll get more into that during class when we talk about amino acids and a lot of the biomolecules. Now, on the other hand, a weak acid only partially dissociates. Okay, so not all of the acid molecules are going to give up their hydrogen ion. It may be 10% or even less. So here's an example of carbonic acid, H2CO3, which we find in soda. Vinegar, acetic acid is another example. It's not a strong acid. It doesn't completely dissociate, and that's why we can use it on foods and actually eat it. So if we have here, let's say that it does dissociate 10%. If we have a 1 molar solution of H2CO3 and it dissociates, we're only going to get a 1/10 molar, a 0.1 molar concentration of the hydrogen ions in that solution. So it's not completely dissociating, it's a weaker acid. Phosphoric acid is another example. It will dissociate from H3PO4 into H+ and H2PO4, but it's not going to completely dissociate, so we're going to get 10% or less concentration of the hydrogen ions in that acid. So there's a difference between strong and weak acids. And here's a diagram that will show pretty well what it is. So if you look over on the left, strong acids are assumed to dissociate completely. So if you look, the two different colored bubbles have completely dissociated. So the red ones, there's your hydrogen ions, they have completely dissociated with the anion, the negative particle ion that they were with. Over on the right-hand side, you'll see most of these molecules are undissociated. Okay, the hydrogen ion is still attached, and there's relatively few of the hydrogens floating around by themselves in there. So the difference between a strong and a weak acid. Okay, real quick, conjugate acid base pairs. What you need to know for this, if you see it, is if we have an acid, so right here HCl, its conjugate base is just what you get when you take away one hydrogen. Okay, so if we take the hydrogen off of HCl, we get Cl minus. So there's the acid and the conjugate base. So if we had H2SO4, if this is the acid, all we're going to do is take one hydrogen away, and what do we get? We get a conjugate base of HSO4 minus. We'll talk a little bit about that. It's not going to be a big deal, but it is something that you should be familiar with as you look at, and just know that the difference between an acid and a conjugate base is just that it loses one proton. And here's an example that you can't really see. Let's see if I can pull this over. There we go, and that's a little bit better. So again, I'm not going to go into great detail here. You may want to pause the video to take a look at it. But if our acid is H2O, what did we say the rule to get our conjugate base? Take a hydrogen away, and we're left with OH minus. Okay, down here, if HCl, we saw this one already, is our acid. We take away the hydrogen, and we get our conjugate base of just the Cl, the chloride ion. Now, let's get into the pH scale. Most of you have probably dealt with the pH scale before, so you know it goes from 0 to 14, with 0 being very acidic and 14 being very basic. 7 is neutral, so pure water should be neutral. Human blood is slightly basic. So if any of you have pools, if you have to, check the pH and keep the pH, a lot of times they tell you to keep it like 7.2 or something, slightly above neutral. So now what we have to be able to do, so here's kind of the math part of it. There are 4 potential values that we can solve for. So there is H+, so this is the hydrogen ion concentration, the hydroxide ion concentration, and then the actual values pH and POH. So you could be given one of those and you would have to solve for the other 3. So here are some things to keep in mind that you should know kind of off the top of your head. So first off, remember that POH, and most of us haven't even dealt with POH before, but it's just a measure of the hydroxide ion concentration instead of the hydrogen, so it's the kind of the opposite of pH. pH plus POH always equals 14. So if the pH is 7, the POH must also be 7, because 7 plus 7 is 14. If the pH is 8, the POH would be 6. They always have to add up to 14. So there's a quick way with the pH and POH. Now the second is the hydrogen ion concentration times the hydroxide concentration always gives you the constant 1 times 10 to the negative 14th. So this allows us, if we know the hydrogen ion concentration, we can solve for hydroxide and vice versa. So there's 2 kind of constants that you should remember. Now the next 2 for both pH and POH, here's the formula. And I'm just going to concentrate right on this one right now because the POH works the same way. But the pH is equal to the negative log of the hydrogen ion concentration. So what that means is that if we have a hydrogen ion concentration of 1 times 10 to the negative 3rd, then what we want to do is we want to take the log of 1 times 10 to the negative 3rd, and if you check your calculator right now, you can pause and go through, you should get negative 3. We're then going to take the negative of negative 3, which comes out to be a pH of 3. Okay, so you need to be able to do that calculation for both the pH and the POH. So here's just a diagram that shows, so here's a low pH, so here's something that would be very acidic down here, so we got lots of hydrogen ions. Got lots of hydrogen on here, and over on the right, we're going to have something that over here would be very basic. We're going to have lots of hydroxide ions over here. So the difference between them, just visually looking at the hydrogen and hydroxide ion concentrations for those. Oh, and let's see if I can fix this for you. There we go. That's a little bit better. So here's some of the calculations that you're going to have to do as we go through and do this. So you might want to pause the video right now, write these down, and get these. So the top 2, we're going to use a little bit. And so here the hydroxide concentration equals 10 to the negative pH. So let's use our example right here. If the pH is 6, then the the hydrogen ion concentration would be equal to 10 to the negative 6. which is going to be the same as 1 times 10 to the negative 6. So that's pretty straightforward. Now, what if it's not an integer? We'll get into that a little bit, and that's where your calculator is going to come in handy. But then we've got the middle two down here. Here's what I said before. Here's the pH and the POH, where it's just going to be the log of the hydrogen ion, the negative log of the hydrogen ion concentration, or the negative log of the hydroxide concentration for that. And then pH plus POH equals 14. So if we keep these in mind as we go forward, we can just solve just about any problem. So let's try an example now. Whoops, I guess we got a diagram here. So this is showing you, there we go. So this is showing you, again, just the pH scale, and the idea that if we start right here at neutral and we go down, if we become more acidic, each unit on the pH scale is a factor of 10. So a 6 is 10 times more acidic than a 7. A pH of 5 is 100 times more acidic than a 7. And as we go up, an 8 is 1/10 as acidic as a 7. So remember that the pH units are logarithmic, and it's going to be a factor of 10 as we change those. Here's the calculations. We'll go over these in class, and I just wanted to have them up here in the video so you can pause and look at it. And now I think we're actually going to get to the example that I wanted to try for that. And let's see if I can get it over into the screen so you can actually see it. There we go. Okay, so here's where we're going to start with this. So in this example, they're giving us the hydrogen ion concentration. So we're going to need to solve for the OH, the pH, and the POH. Now, there's more than one way to do this. There's many ways, and as long as you understand, you're good. I'm going to show you one way for me. So in this example, if I know the hydrogen ion concentration, I know that H plus times OH minus, see if I can get my, there we go, OH minus is always equal times 1 times 10 to the negative 14th. So if I know that this is 5.6 times 10 to the negative 9th equals 1 times 10 to the negative, oops, no. I can divide both sides by 5.6 times 10 to the negative 9th. 5.6 times 10 to the negative 9th. There we go. Those will cancel. And OH is equal to 1 exponent negative 14 divided by 5.6 exponent negative 9, and I get an answer of 1.8 times 10 to the negative 6th molar. So there's my OH, so I've got 1. So now I know that my hydrogen ion concentration is 5.6 times 10 to the negative 9th. So let's get our pH. So our pH is going to be the negative log of 5.6 times 10 to the negative 9th. So 5.6 exponent negative 9, take the log. I get negative 8.25. I'm going to take the negative of negative 8.25. So our pH becomes 8.25. Now the last piece of the puzzle, I need to find the POH, and I know that pH plus POH has to add up to 14. I just found that my pH was 8.25 plus the POH equals 14. Subtract 8.25 from both sides, and 14 minus 8.25 equals POH of 5.75. So there we go, and that's what you're going to be responsible for. If they give you any one value, you need to be able to solve for the other 3 values. And as we said, we'll have lots of practice in class and chance for you to ask questions. Thanks for your attention.